Think about the last time you actually noticed the sun. Not glanced at a clock and registered that it was daylight. Actually stopped and noticed it. Most of us can't remember. It's too familiar to see. It's been rising every morning for every human who ever lived, and somewhere along the way, it became invisible. Background radiation, a scheduling tool, but suppose it didn't rise tomorrow. Not an eclipse, those last minutes. Suppose the sun simply wasn't there. Day 1 would be cold and strange. Day 2, the oceans would begin to freeze at their surfaces. Within a week, most plant life would be dead. Within a year, the average surface temperature of Earth would drop below -70 degrees. The atmosphere itself would eventually freeze out of the sky and settle as a thin frost on the ground. We have never truly experienced the sun. We've only ever lived inside it. The sun is not a nearby lamp. It is a star, and it behaves like one. Its output, the total energy it radiates in every direction every second, is expressed as a number with 26 zeros after it, measured in watts. A single light bulb runs on 100 watts. A city on a few gigawatts. The sun puts out more energy every second than humanity has generated in its entire history. Every second continuously for 4.5 billion years. To understand what that means in physical terms, Earth intercepts only 1/10 billionth of the sun's output. That sliver, that vanishingly small fraction, is enough to run every weather system, every ocean current, every living thing on this planet. It drives the jet stream. It evaporates the water that falls as rain. It powers, ultimately, everything we eat. Now consider what would happen if you could redirect the entire output onto Earth. Just focus it, the way a child focuses sunlight through a magnifying glass onto a dry leaf. The oceans would not merely boil. They would boil away, completely evaporated into space. It would take about 4 minutes for the oceans to begin vaporizing. 10 days for Earth itself to be reduced to individual atoms adrift in space. No crater, no debris field, just atoms where a planet used to be. This is the object that shares our sky with pigeons and power lines. And then there's the question of scale. We know intellectually that the sun is large, but our intuitions don't process it correctly. The sun's diameter is about 109 times Earth's. You could fit more than 1 million Earths inside it by volume. Even Jupiter, which is itself 10 times the diameter of Earth and 1,000th the mass of the sun, looks like a pea next to a basketball when placed beside the sun at the same scale. Saturn, with its rings spanning hundreds of thousands of kilometers, would be similarly dwarfed. The entire collection of planets, moons, asteroids, and comets orbiting the sun accounts for less than 1/5 of 1% of the total mass of the solar system. Everything else is the sun. It doesn't share the solar system. It is the solar system. The planets are debris orbiting a star. The sun's gravity is what keeps them in place, and its light is what makes the whole arrangement visible to us. But that light, useful and beautiful as it is, comes with a warning. Looking at the sun directly is not like looking at something bright. It is more like pressing a hot iron against your retina. The photoreceptors in the eye are extraordinarily sensitive, sensitive enough to detect individual photons from stars that are light years away. The sun is not light years away. It is 8 light minutes away, and it floods your eye with 1 million times more light than it can safely handle. Damage can happen faster than pain can register. The retina has no pain receptors. You won't feel it happening. By the time the brain processes any sensation of discomfort, the cells are already dead. This is why solar observers are almost obsessively careful. Simple dark sunglasses, the ones you'd wear on a beach, offer almost no protection against the sun itself. They're designed for scattered, diffuse light on a bright day, not for direct solar radiation. The filters needed to safely observe the sun block more than 99.9% of incoming light. Even then, only a tiny fraction gets through. Telescopes without such filters are far more dangerous than bare eyes. They concentrate the light, focusing it to a point that can scorch through an eyepiece like a blowtorch. A solar astronomer's workshop joke. You can look at the sun through a telescope twice in your life, once with the right eye, once with the left. The safest method of solar observation requires nothing more than a piece of cardboard and a pin. Make a small hole, a few millimeters across, and hold it up so sunlight passes through and falls on a surface behind it. A sheet of paper, a white wall. The hole acts as a pinhole camera, forming a real inverted image of the sun. It's small and dim, but it's accurate. During a solar eclipse, this simple setup shows the moon's disk advancing across the sun with perfect clarity at zero risk to your eyes. The method is over 2,000 years old. It has never been improved upon for sheer safety. But seeing the sun is not the same as understanding it. For most of human history, we could observe the solar disk and nothing more, a featureless coin of light, too bright to examine, too important to ignore. We did not know what it was made of. We did not know where its energy came from. We did not know how old it was or how long it would last. We called it a god and moved on. The first real crack in that ignorance came not from a telescope, but from a prism. In the early 19th century, a Bavarian optician named Joseph von Fraunhofer was studying the spectrum of sunlight, the rainbow you get when you pass white light through a glass prism. He expected a smooth, continuous band of color running from violet to red. What he found instead was a rainbow interrupted by hundreds of thin, dark lines, each at a precise and repeatable position. He cataloged them methodically. He gave them letters. He had no idea what they were. The explanation arrived decades later. Every element absorbs light at specific wavelengths, each one a unique set, like a fingerprint. When sunlight passes through the cooler outer layers of the sun's atmosphere on its way to us, certain wavelengths are absorbed by certain atoms and removed from the spectrum. The dark lines Fraunhofer saw were the fingerprints of those atoms, stamped into the light before it left the sun. By matching the pattern of lines to elements tested in the laboratory on Earth, scientists could determine what the sun was made of without going there, without touching a sample. Without anything more than a beam of light and a glass prism. This technique, spectroscopy, became the master tool of astrophysics. It is still how we determine the composition of every star we observe. Every atom has a signature. Every signature is readable in light. One of the elements detected in the solar spectrum in the 1860s did not match anything known on Earth. It was named helium after Helios, the Greek sun god, because it was found in the sun 27 years before it was discovered on Earth. The universe was telling us what it was made of. We just had to learn to read the message. The reading revealed something unexpected. The sun is overwhelmingly hydrogen, not a mix of elements in roughly the proportions found in rock, as most scientists had assumed, but almost entirely the lightest and simplest element in existence. In 1925, a young British astronomer named Cecilia Payne analyzed stellar spectra for her doctoral thesis and reached exactly this conclusion. The established authorities of the field told her she was wrong. The result was, as one senior astronomer put it, almost certainly not real. She was persuaded to qualify her own findings in the final text. 4 years later, the same authority reached the same conclusion through independent analysis and published it as his own discovery, without qualification. Payne had been right. The composition of the sun had been determined by a 25-year-old woman who was then told to doubt herself. She eventually received the recognition she was owed. The sun's composition did not change in the meantime. Knowing what the sun is made of immediately raised a sharper question. What is it burning? By the late 19th century, the geological record made it clear that Earth was hundreds of millions of years old at minimum. The sun had to have been shining for at least that long. Physicists calculated that if the sun were made of coal and burning in oxygen, it would have exhausted its fuel in a few thousand years. Some proposed that the sun was slowly contracting under gravity, converting gravitational energy to heat, but that mechanism could only sustain the sun for about 20 million years, far less than the geological evidence required. The numbers did not add up. Whatever was powering the sun, it was not any process known to 19th century physics. The answer arrived with nuclear physics in the 20th century. At the center of the sun, the pressure is approximately 250 billion times atmospheric pressure, and the temperature is around 15 million degrees. Under these conditions, hydrogen nuclei, bare protons, are forced close enough together to fuse. Through a sequence of reactions, 4 protons combine to form a helium nucleus. The helium nucleus weighs slightly less than the 4 protons that formed it. That missing mass does not vanish. It is converted directly into energy, according to the equation Einstein published in 1905. The mass deficit is less than 1%. But the sun contains so much hydrogen, and the conversion is so efficient, that 4 million tons of mass are transformed into pure energy every single second. 4 million tons per second. The sun has been doing this for 4.5 billion years, and it has enough hydrogen remaining to continue for approximately another 5 billion. The nuclear furnace at the sun's core is the reason everything lives. It is also, in a specific way, a remarkable accident of physics. The fusion rate is exquisitely sensitive to temperature. If the core heats slightly, fusion accelerates, producing more pressure, which expands the core slightly, which reduces the density and temperature, which slows fusion back down. The sun self-regulates like a thermostat. This stability is not a universal property of all stars. It is a specific feature of stars in the main sequence phase of their lives, and it is what makes billion-year planetary habitability possible. A star that flickered on decade timescales would sterilize its planets with each pulse. Here is one of the stranger things about the sun's interior. The energy produced in the core does not travel quickly to the surface. Light crosses the 93 million miles from the sun to Earth in 8 minutes. The energy generated in the sun's core takes somewhere between 10,000 and 100,000 years to reach the surface. The reason is density. The core is so compressed that a photon of light, traveling at the speed of light, cannot go more than a centimeter before being absorbed and re-emitted by a charged particle. It staggers outward in a random walk, absorbed and re-radiated millions of times, bouncing in all directions at once, making negligible net progress. This layer, the radiative zone, extends from the core out to about 70% of the solar radius, and it is effectively opaque. Light doesn't travel through it so much as diffuse through it, the way smoke spreads through a closed room. The light warming your face right now left the sun's core somewhere between 10,000 and 100,000 years ago. When that energy began its journey, modern humans had barely arrived in Europe. Neanderthals were still alive. Woolly mammoths roamed Siberia. The photon has been ricocheting through the solar interior ever since, finally reaching the surface a few minutes ago and crossing to you in the time it takes to drink a cup of coffee. Beyond the radiative zone, the gas becomes less dense and convection takes over. Hot material rises, cools at the surface, and sinks back down, the same motion as a pot of water on a stove, operating at 6,000 degrees across a sphere larger than 1,000,000 Earths. This convective zone delivers energy efficiently to the surface. There is a way to look inside the sun that does not involve light at all. In the 1960s, astronomers noticed that the solar surface oscillates. The entire star pulses in and out in overlapping rhythms, millions of distinct vibrational modes, like a bell struck by an invisible hammer. Each mode is a pressure wave resonating through the solar body. The individual oscillations are far too low in frequency for human ears to detect, but sensitive instruments can measure the tiny Doppler shifts in the spectrum as the surface moves toward and away from Earth. By analyzing this cacophony of overlapping waves, a field called helioseismology, researchers can probe the sun's interior the way geologists use earthquake waves to map Earth's crust and mantle. The rotation rate at different depths, the temperature gradient, the boundary between the radiative and convective zones, all of it reconstructed from sound. It is one of the most elegant techniques in modern science. Using acoustic waves to see inside a star 93 million miles away. The surface of the sun, the layer we see called the photosphere, from the Greek word for light, is not smooth. It is not a calm, featureless ball of fire. At high magnification, it looks like the surface of a pot of oatmeal brought to a slow boil. It is covered with a shifting, seething pattern of bright cells, each one roughly the size of a small European country, surrounded by slightly darker borders. These structures are called granules. Each granule is a column of hot gas that has risen from deeper inside the sun, pushed upward by buoyancy, reached the surface, released its heat into space, cooled slightly, and begun to sink back down. Then the cycle repeats. This is convection operating at planetary scale, at 6,000 degrees, with timescales of about 10 minutes per cycle. The surface is never still. Every granule you see is a temporary structure, born and gone within the time it takes to watch a short film. Against this backdrop of boiling brightness, there are larger, darker regions, sunspots. They are not dark in any absolute sense. If you could isolate a sunspot and look at it alone, it would outshine any artificial light source ever built. But they are cooler than the surrounding photosphere by roughly 1,500 degrees, and that temperature difference is enough to make them appear almost black by contrast. They have structure. Each large sunspot has a central core, the umbra, from the Latin for shadow, which is the coolest and darkest part. Around it sits a broader transitional region called the penumbra, with a streaked, fibrous texture caused by magnetic field lines, pulling the gas into filaments. The whole complex looks, under a good telescope, something like a vast, shallow pit in the solar surface, with material cascading inward along the edges like a slow, burning whirlpool. They are caused by the sun's magnetic field. The sun generates magnetic fields through the motion of its electrically charged interior, a process called the solar dynamo. In most places, this field is relatively weak and diffuse, but in certain regions it becomes intensely concentrated, and intense magnetic fields have a specific effect on hot plasma. They block it. They prevent the convective churning that normally brings heat to the surface. Hot gas from below cannot push through the field lines, so those regions are starved of their heat supply and cool down. The cooled gas is denser and sinks. You end up with a depression, a magnetic cap, and a surface that radiates less light than everything around it. That is a sunspot. Some sunspots are small and fleeting, lasting only a day or two. Others grow enormous, larger than Earth, sometimes much larger, and persist for months. As the sun rotates, these long-lived spots sweep across the visible disk and then disappear around the edge, returning into view nearly a month later, changed but recognizable. Ancient Chinese astronomers recorded them. Medieval European monks noted them, confused by what they saw. Galileo used them to demonstrate that the sun rotated, which was itself a controversial claim. The sun was supposed to be a perfect, immutable celestial body. Sunspots were proof that it was not. They were the first evidence that the sun had a history, a changing surface, a physical process occurring in real time. The rotation they reveal is peculiar. The sun does not spin as a solid body. At the equator, one rotation takes about 25 days. Near the poles, it takes closer to 35. This differential rotation, the equator perpetually lapping the poles, has a consequence. The magnetic field lines threading through the solar interior are dragged along with the rotating plasma. Over months and years, the field lines are progressively wound up, stretched, tangled, twisted. Eventually, in certain regions, the tangling becomes critical and concentrated bundles of field lines erupt through the surface. Sunspots appear in pairs with opposite magnetic polarities, one end of a buried magnetic arch breaking through the surface, arching across and re-entering nearby. Tracking sunspot polarities over successive 11-year cycles reveals another pattern. The leading polarity in each pair flips from one cycle to the next. The full magnetic cycle of the Sun is not 11 years but 22, the time required for the field to wind up, release, and re-establish itself with the same polarity it started with. Track the total number of sunspots from year to year, and something unexpected appears. The count is not random. It rises and falls in a rhythm. Roughly every 11 years, the Sun moves from a state of maximum activity, many large, complex spot groups spread across the disk, to a state of minimum activity when the surface can be clean and featureless for weeks. Then it builds again. This solar cycle has been documented continuously since the mid-18th century. The historical record, assembled from observations going back to Galileo's time, contains longer patterns as well, including a period between roughly 1645 and 1715, when sunspots nearly vanished for decades. Astronomers call this the Maunder minimum. It coincided with a period of unusually cold winters across Europe and North America, known as the Little Ice Age. The connection is still debated, and the climate system is complex, but the overlap is not easily dismissed. What happens on the Sun does not stay on the Sun. The sunspots are indicators, not causes. What they mark is something deeper: the state of the Sun's global magnetic field. When spots are numerous, the field is tangled and energetic. When spots are absent, the field is relatively smooth. And when the field is tangled and energetic, other things happen, things more dramatic than spots. Sometimes the stored magnetic energy releases catastrophically in an instant. A solar flare is a magnetic short circuit. Field lines of opposite polarity that have been wound together snap into a lower energy configuration, converting magnetic energy directly into heat, radiation, and fast-moving particles in a matter of seconds. The energy released in a major flare equals roughly 100 million hydrogen bombs. The flash of radiation travels at the speed of light and reaches Earth in 8 minutes. Radio communications on the sunlit side of the planet are disrupted almost immediately. Signals from GPS satellites degrade. High-frequency radio used by aircraft crossing polar routes can fail completely for hours. All of this from an event occurring 93 million miles away, too small to see with the naked eye against the solar disk. Along the edges of the solar disk, especially visible during eclipses, vast arches of glowing plasma rise above the surface and loop back down, tracing the invisible curves of magnetic field lines. These are prominences. Some are stable structures hanging suspended for weeks, anchored at both ends by the field and glowing with the steady light of hydrogen. Others erupt suddenly, the magnetic field destabilizes, snaps, reconnects in a new configuration, and releases enormous energy in seconds. The gas is launched upward at hundreds of kilometers per second. If the eruption is contained, the plasma rises, slows, and falls back, raining onto the solar surface in curtains of fire. If it breaks free, it escapes the Sun entirely. When it escapes, astronomers call it a coronal mass ejection. Billions of tons of magnetized plasma hurled into space at speeds of 1 to 3,000 kilometers per second. Not a continuous flow, a wave. A magnetic shock wave followed by a dense cloud. These events happen several times a day during solar maximum. Most go in directions that miss Earth entirely, but roughly once or twice per solar cycle, one heads directly toward us. Above the photosphere, above the prominences, above the chromosphere, sits the Sun's outermost atmosphere, the corona. In ordinary daylight, the corona is completely invisible. The photosphere is so blindingly bright that the corona, despite being millions of kilometers across, is simply washed out. You can see it only during those rare minutes of a total solar eclipse, when the moon covers the disk exactly, What appears then is startling. Not a faint glow around the edge, but a complex structured halo of pale white light, with streamers extending outward for several solar diameters, like the arms of a slow, frozen explosion. Ancient peoples who witnessed total eclipses without knowing what caused them were genuinely terrified. The corona looks like nothing else in the natural world. To see the corona without waiting for an eclipse, astronomers build coronagraphs, telescopes fitted with an internal disk that blocks the photosphere artificially, creating a permanent artificial eclipse for the instrument. The sun that appears in coronagraph images looks nothing like the noon sun. It is a dynamic structure of loops, arches, and outflowing streams, constantly reorganizing, constantly shedding material into space. Some regions, coronal holes, where the magnetic field opens outward rather than looping back, appear dark because the plasma there escapes freely rather than accumulating. These holes are the main sources of the fast solar wind. The sun, seen in the right light, at the right wavelength, never stops moving. And the corona has a property that still resists full explanation. It is extraordinarily hot. The photosphere, the surface, sits at about 6,000 degrees. Moving upward through the chromosphere, the temperature drops, as you would expect from any normal heat source. Then something strange happens. The temperature starts rising again. By the time you reach the corona, it has climbed to over 1,000,000 degrees. The corona is roughly 200 times hotter than the surface it sits above. This seems to break a fundamental rule. Heat flows from hot to cold, not the other way. If you walk away from a bonfire, you get colder. You don't spontaneously become hotter than the fire itself. Yet the sun's corona does exactly this, or appears to. Something is delivering energy to the corona that doesn't pass through the photosphere in the usual way. The current leading hypothesis involves the magnetic field. Waves traveling along field lines dissipate their energy as heat when they reach the corona. A second mechanism involves small, rapid magnetic reconnection events, nanoflares too tiny to see individually, but contributing to coronal heating in aggregate. Neither explanation is fully confirmed. The corona temperature problem has been known since the 1940s, and it remains genuinely open. This is not a case of scientists saying they don't know exactly how something works. It's a case where the basic mechanism is contested. In 2018, NASA launched the Parker Solar Probe specifically to gather data from inside the corona. At its closest approach, it passes within 6 million kilometers of the solar surface, closer than any previous spacecraft, moving at nearly 700,000 kilometers per hour, fast enough to travel from New York to London in under a minute. Its heat shield must withstand temperatures above 1,000 degrees Celsius, while the instruments it protects operate at room temperature, just centimeters behind it. The probe has already detected structures in the solar wind nobody predicted, tight, sudden reversals in the direction of the magnetic field, occurring repeatedly as the probe crosses the corona. Researchers call them switchbacks. They are not understood. The sun continues to produce surprises for every instrument pointed at it. The corona doesn't just sit there, mysteriously hot. It expands. The outer corona is too hot and moving too fast to be held in place by the sun's gravity. It streams outward continuously in all directions, a permanent wind of charged particles, mostly protons and electrons, flowing through the solar system at 400 to 800 kilometers per second. By the time this solar wind reaches Earth, 8 minutes away at light speed, but 3 or 4 days away at solar wind speed, it has thinned considerably. But it hasn't stopped. It fills interplanetary space constantly, pressing against every planet, sweeping the tails of comets always away from the sun, regardless of which direction the comet is actually traveling. The solar wind shapes the solar system's environment in ways we are still mapping. The boundary where the solar wind finally loses its fight against the interstellar medium, the thin gas between the stars, is called the heliopause. It sits roughly 18 billion kilometers from the sun, give or take depending on the direction. The Voyager 1 spacecraft, launched in 1977 and still transmitting data, crossed that boundary in 2012, becoming the first human-made object to enter interstellar space. What it found at the boundary was not a sharp edge, but a turbulent transition zone, where the solar wind piles up and slows before giving way entirely to the interstellar flow, pressing in from outside. The sun's domain is vast, and its edge is complicated, but there is an edge. Earth, fortunately, has a magnetic field of its own. The field deflects the solar wind around the planet, forming a protective envelope called the magnetosphere, a bubble compressed on the sunward side and stretched into a long tail on the night side, like a comet in reverse. Most of the charged particles never reach the surface. But the magnetosphere is not perfectly sealed. It has two soft spots, funnel-shaped regions over the magnetic poles where the field dips inward toward Earth. At the poles, charged particles follow field lines downward into the upper atmosphere at altitudes of 300 to 600 kilometers. When they arrive, they collide with atoms of oxygen and nitrogen. The collisions excite the atoms, pushing electrons to higher energy levels. When those electrons drop back down, they release photons, light. Oxygen at high altitude emits red. Oxygen at lower altitude emits green. Nitrogen contributes blue and violet. The precise mix depends on the altitude, the density, and the energy of the incoming particles. The curtains of light shift and fold because the particle streams are structured, not uniform, ribbons and sheets of plasma arriving at slightly different velocities, following slightly different field lines. This is the aurora, the northern lights, the southern lights, a direct visual signature of the sun's influence painted on the upper atmosphere by charged particles that left the sun 3 or 4 days ago. Auroras are beautiful. They are also a warning sign. The stronger the solar activity, the more intense the aurora, and the more intense the disruption to everything in near-Earth space. In 1989, a major solar storm knocked out power across the entire province of Quebec, leaving millions without electricity for 9 hours. In 1959, an event now called the Carrington Event, the largest solar storm in the historical record, induced currents so strong in telegraph lines that some operators reported sparks flying from their equipment. Some lines caught fire. Operators reported that their equipment worked even after being disconnected from the power source, running on the induced current alone. If a Carrington-scale event happened today, the damage to satellite infrastructure, power grids, and communication systems has been estimated in the trillions of dollars. The disruption would be global. Recovery would take months, possibly years. This is not speculation. It is a matter of historical record and statistical probability. Events of that magnitude appear to occur roughly once per century. The last confirmed one was 1859. The infrastructure that would be destroyed today simply did not exist in 1859. The gap between what modern civilization requires and what the sun occasionally delivers is not theoretical. At 400 kilometers altitude, directly in the zone where auroras form, the International Space Station orbits. Astronauts on board are above the bulk of Earth's protective atmosphere. They receive radiation doses that accumulate over the course of a mission and require careful monitoring. During a major solar event, they face a real decision: shelter in the most shielded section of the station, reduce operations, and wait. Ground controllers track solar activity continuously for exactly this reason. The sun's behavior on a Tuesday afternoon can determine whether an astronaut on Thursday goes outside to conduct a spacewalk or stays inside. This is why solar forecasting exists as a field. This is why spacecraft are positioned at the L1 Lagrange point, a gravitational equilibrium between Earth and Sun, about 1.5 million kilometers toward the Sun, where they can detect the solar wind 45 minutes to an hour before it reaches us. That is the advance warning time for most solar events. 45 minutes. In that window, Satellite operators can put instruments into safe mode. Power grid operators can prepare for load fluctuations, and space agencies can assess crew safety. It is not a comfortable margin, but it is what physics allows. There is one more thing the sun produces that we almost cannot catch, but that turned out to matter enormously for physics. Neutrinos. The fusion reactions in the core generate vast quantities of these subatomic particles, which interact with ordinary matter so weakly that they pass through the entire body of the sun without stopping. They pass through Earth. Roughly 65 billion solar neutrinos cross every square centimeter of your skin every second day and night. At night, they arrive from below, having passed straight through the planet first. You have never felt one. For decades, this created a serious problem. When physicists built the first detectors capable of catching solar neutrinos, vast underground tanks of cleaning fluid, shielded from cosmic rays by kilometers of rock, they counted far fewer than the sun's fusion models predicted, about a third as many. Either the models were wrong, or the neutrinos were somehow disappearing in transit. This became known as the solar neutrino problem, and it nagged at physicists for 30 years. The resolution required a revision of fundamental particle physics. Neutrinos come in 3 distinct types, and they oscillate between types as they travel, changing identity en route from the sun's core to an underground detector on Earth. The original detectors could catch only one variety. The other 2/3 were arriving perfectly on schedule, in forms the instruments were blind to. Solving the solar neutrino problem required accepting that neutrinos have mass, something not previously established, and earned 2 physicists the Nobel Prize in 2015. The sun, studied as an astronomical object, had forced a correction in the standard model of particle physics. The closest star turned out to be the most useful particle accelerator in the solar system. The sun has been burning for 4.5 billion years. It will continue for approximately another 5 billion. But it will not continue in the same way. As fusion converts hydrogen to helium in the core, the helium accumulates, inert at current temperatures, unable to fuse further. The proportion of hydrogen in the core slowly declines. The sun's response over geological timescales is to contract the core and expand the outer layers. This is already happening. The sun today is about 30% more luminous than it was when Earth formed. Within a billion years or two, the increased output will likely make Earth's surface uninhabitable, oceans evaporating, the planet's water escaping to space, surface temperatures climbing beyond anything biology can tolerate. Eventually, the hydrogen in the core runs out entirely. The core contracts under gravity, heats up, and ignites fusion in a shell surrounding it. This additional energy source causes the outer layers to expand, not a little, but dramatically. The sun will swell into a red giant, growing to perhaps 150 times its current size. Mercury will be engulfed. Venus will be engulfed. Earth's fate is uncertain. The sun's mass loss during this expansion may cause Earth's orbit to drift outward fast enough to stay ahead of the expanding surface, or it may not. Either way, the surface will be scorched to bare rock long before the red giant phase peaks. Then the helium in the core, compressed by the contracting hydrogen fusion shell above it, reaches the temperature needed for helium fusion. The ignition is explosive, a helium flash releasing in seconds more energy than the sun generates in 1,000,000 years. The star briefly reorganizes and settles into a new phase, fusing helium to carbon and oxygen in its core. This phase is shorter than the hydrogen-burning main sequence. Helium is a less abundant fuel, and it burns faster. Eventually, it too runs out. What follows is not an explosion, but an exhalation. The outer layers drift away over thousands of years, forming an expanding shell of glowing gas called a planetary nebula. The term is historical and misleading. It has nothing to do with planets. What remains is the core, a dense, Earth-sized sphere of carbon and oxygen, no longer fusing anything, radiating stored heat into space. a white dwarf. It will cool for billions of years, dimming from white to yellow to orange to red to a darkness that cannot be observed because the universe has not yet been old enough for any white dwarf to cool that far. The entire story, from the collapse of a molecular cloud to a cooling cinder, takes about 10 billion years to tell. We are at the halfway point. The star that makes our air warm and crops grow also emits radiation that can destroy retinas in seconds, and plasma storms that can collapse power grids across continents in minutes. It has been burning since before multicellular life existed on Earth. It will still be burning long after any conceivable human civilization has risen, fallen, and been forgotten. It answers to no schedule we set. It doesn't know we exist, and yet understanding it, its rhythms, its outbursts, its still unresolved mysteries, has become one of the most practically urgent problems in modern science. Not because the universe is threatening us, but because we have built a civilization whose nervous system runs on electricity, and we live 8 light minutes from a star. We orbit it. We depend on it completely, and we are still learning what it actually is.